Today I will discuss about Galactic Swarm Optimization. So this is a very easy optimization algorithm which mimics the gravitational pull that exists in between galaxies, subgalaxies, solar systems and planets. So what actually happens is you know suppose our planet Earth, this Earth is located into where? This Earth is located into solar system. It rotates around the sun along with other 8 planets. So Earth is located under solar system. Now this solar system is again located under the Milky Way galaxy, correct? And Milky Way galaxy is located under this Milky Way galaxy was located under a super galaxy known as Virgo supercluster. Virgo supercluster. Now Virgo supercluster is again located under another super galaxy, and so on. And there are millions of super galaxies, under which millions of sub galaxies are there. Under the sub galaxies there are millions of galaxies, and under the galaxies there are billions of solar systems, and under the solar system there are many planets that exist, but all are rotating among each other or by centering some sun-like what I would say stars due to the gravitational pull, because sun is pulling Earth, and this not only Earth, it is pulling Mars, it is pulling Mercury, it is pulling Jupiter and all other planets. And the sun is being pulled by Milky Way galaxy, right? This is a spiral galaxy, big spiral galaxy, and it is the second largest spiral galaxy that exists in the observable universe. Actually, we assume that there is one non-observable that we cannot, or until now no telescope has been able to observe that part of universe. That part of universe is defined as non-observable universe, and which the telescope has already observed. Any type of telescope, be the first one invented by Galileo Galilei, be the most advanced one, any type of telescope, if it has observed that part of universe, it comes under the observable universe. Now all these Earth, Sun, Milky Way, Virgo, then we have something as Landraker. All these are observable, part of observable universe. Now I have already said that they are all aligned with each other due to the gravitational pull. Now what happened is, this optimization algorithm, yes, this can be referred as nature based, but not bio-inspired, because here, as you can see, there is nothing biology here. So it is nature based, right? Because it is the nature which is creating all these pools and all this alignment and all these things. So what it assumes is, it assumes that, say, the entire feasible region of optimization problem or the solution space from where we can expect to find the most optimal solution can be compared with or can be analogous to super galaxy, correct? Super galaxy. Now, what happened? Within this super galaxy, we create at random basis some subpopulation or population, I would say. Population of probable solution P. We refer it as P, right? So they are analogous to galaxy. So solution space, you see, this is your solution space, correct? So this is analogous to super galaxy. And under that, these are the population that was created randomly. Say, these are the subset of the super galaxy that are created, or population of probable solution created under the solution space. Now, under this solution space, there are again some subpopulations are created. They are known as subpopulation of probable solution, right? But this subpopulation of probable solution is better than the population of probable solution, but exists within this population of probable solution. So they are analogous to solar system. And the optimal solution with respect to the population of or the subpopulation of probable solution is known as the planet, like our Earth. Okay. Now what happens is, we can identify the planets of all the subpopulation, from which, say, this is our most optimal solution for this population or subpopulation, or the optimal solution. This is the set. As I say, first is the solution space, then come your population of probable solution, then if I enlarge this part, then come your probable of subpopulation of probable solution, and within that there will be some most optimal solutions, correct? Most optimal solution can be found from the subpopulation. Now if I compare this most optimal solution, this most optimal solution, this most optimal solution, this most optimal solution, where I compare with each other, this solution with this solution with this solution with this solution, then you will find the best solution or the planet, right? Best solution of this part of subpopulation. But this best solution of the best planet, you can find it here also for this subpopulation, here also for this subpopulation, and here also for this subpopulation, right? So for each subpopulation, I will get an optimal solution or a planet, optimal planet. Okay, and for If I compare those planets with each other, then I will get the best solution of the population. And as there are randomly many population within a solution space, and if I compare all that optimal solution of those population, then I can find the best solution among the entire solution space. This is a very confusing concept, but very, very easy concept. Let us repeat it. Suppose this is our solution space. What do we do at the initial stage? We divide it into different random population of probable solution. And then this is also randomly divided into subpopulation. You see, this is the population, this is the subpopulation, and then within this subpopulation there will be optimal solution. Okay, and this optimal solution is actually the best solution among this entire subpopulation and among this entire population, right? Because what I have said that for each of these subpopulation we will have a best solution, correct? All these subpopulation will create a best solution. And if I compare all this best solution of the subpopulation, I will get the best solution of the entire population. And for this there will be, right? For each population I will have a best solution. And then if I compare these things, the best solution of the populations, then I will get the best solution that exists in between these, what I can say is the solution space, entire solution space. Okay, the advantage of this type of algorithm is that each and every space within the solution space or feasibility region can be explored. Okay, so when we are dividing the spaces into different population, subpopulation, and within the subpopulation we are trying to find the optimal solution, these are all exploration, they are saying, right? So up to the part where we are dividing the domain into different population, different subpopulation, and ultimately we find the optimal solution for the subpopulation. Before that, it is exploration. The moment I find the optimal solution, I am into the exploitation phase. As you know, all nature-based or bio-inspired optimization algorithm has two phases. One is your exploration, another is your exploitation. In case of exploration, we explored the solution space. Like we explored Indian subcontinent, we explored Calcutta, we explored Delhi for knowing where the best location to visit, best tourist places exist, in which place. So we have to use some such mechanism. So when we are searching, we are exploring. When we have identified the probable best places, best solutions, that means we have the alternatives with us. Then when we are comparing it to find the best among the best, then that is known as exploitation. And for exploration, exploitation, in each phases, there will be one fitness function which will actually guide you towards the optimal region or optimal solution. So let us take this problem. This is an example problem. Maximize y is equal to x square. Subject to x can take the value of 0 and 1 only. Sorry, 0 to 1 only, but not 0, not 1. You see, there is no equality here, only inequality. So x can take any value from 0.001 to 0.9999 like this. Correct? So within this point, I have to find the best solution that will create the maximum or give me the maximum value of y. So as you know, this y is equal to x squared. This part is known as objective equation. This x is our design variable. I think these are all known to you. And this y is the objective variable. And subject to 0 to 1 x, this is known as constraints. Both ways it is bounded by two inequality constant. So it is known as bounded constraint or bounded optimization problem, because both way it is bounded. If one right hand or left hand side is open, then it is known as unbounded optimization problem. So this is the problem. And let me see how I can solve it with the help of Galactic Swarm Optimization Technique. So this part I have already discussed. As I said, this is the super galaxy, which is equivalent or analogous to the solution space. Okay, and then we are randomly dividing it into different population of probable solutions, right? So this can be analogous to galaxy, and then these probable solutions are subdivided into subpopulation of probable solution, which I can compare with solar system, and then this subpopulation is cultivated or explored to find the optimal solution, and this can be compared with our planets. Like Earth is the most optimal planet. Now, until we are searching different places within this solution space, we are exploring. But when we are comparing the best solution of different subpopulations, and then best solution of different population, and then best solution of the different population will give you the most optimal solution that exists in the solution space. This has already been discussed in the previous slide. So this phase is known as exploitation phase. The moment we are comparing the best solution among each other, sorry, we have entered into the exploitation phase. Now another question is that how to search, right? So for searching, you can use any deep search algorithm like PSO, you can read particle swarm optimization, genetic algorithm, and colony optimization. I have the videos of them also. You just go to my YouTube channel and subscribe. So PSO can be used, and colony optimization can be used. GA, genetic algorithm, can be used, correct, to search for the best solution. And once identified, they will compare with each other to find the most optimal solution that exists in the solution space. So I have here divided the working procedure into the exploration and exploitation. As you can see, I will not repeat this. What is exploration and what is exploitation, and this is the tips or note. This is not part of anything. You can use any type of search algorithm, PSO, GA, SU, etc. Okay. Now, the explanation I have already explained it, but let us solve this problem. Y is equal to x square. This is going to be max. I have 0 to 1. That means x can take more than 0, less than 1 value, anywhere. So they are not mentioned that whether only integer or fraction. So let it be any real number I can take. Let us assume that. Okay. So how we'll start it? Okay. First I have said Solution space is defined here 0 to 1, correct? Within 0 to 1, this is x, this is y. So within this 0, suppose this is 1, so solution domain exists here, right? This is basically the solution. This part I cannot here, this is anywhere because it will depend upon the x only. So, but this is my solution domain. So this is our super galaxy, correct? Now what I will do, I will try to randomly divide this solution space into uh, sub galaxy or sub population of probable solution. So let me say that this is the you can say it as sub galaxy, right? So sometimes what happens if you are not using this sub galaxy, you can directly move into the galaxy. So but for now, let me go with the sub galaxy. So super galaxy, sub galaxy, then galaxy, yes, then solar system, then the optimal solution, that is planet. All pulled by the gravitational, all aligned by the gravitational pull. Okay. So what happens is, so this is my solution space super galaxy. So for sub galaxy, I will randomly divide this solution space. But for example, I am dividing it very uniformly into 4 parts. This is just an example, that is why I am doing it uniformly, but it actually happens randomly. Randomly you can divide it. So how to divide this space like this? So let me divide this space like this. This is our first population, second population, third population, fourth population. So let us see 0 to 0.25. This is the first population. 2625, then 0.51 to 0.75, right? 0.7621. So I cannot take 0, so I will use it at 0.1, and I cannot take 1, use it at 0.99. Correct? Now this has been taken place. Now what I will do, this is super galaxy, sub galaxy, right? To create galaxy, what I will do, I will again divide this domain, that is 0 to 0.25, this domain 0 to 0.25 into 4 parts. I am saying this is randomly taken. You can divide it into 4, or you can 8, or you can 12, it is up to you. But 4 parts we have divided. Okay, so, and all are equal, I am assuming. So if you divide this 0.25 by 4, so you can get from where to where you can take the domain, right? So if I go about, I think 0.06, so 0 to 0.06, then 0.013, like this. You can take, I will not take much time, so that is why I am not showing it in detail. So in this way, you can divide 0 to 0.25 into 4 domains, and then 0.26 to 0.5, and then 0.5 to 0.7, and so on. Correct? Next step is that you are now in the galaxy phase, because from super galaxy you have done this sub galaxy, then from sub galaxy you have gone this galaxy, and now we are coming into solar system. Correct? So solar system, so as usual, again divide, so 0 to 1 was divided into 4 parts, correct? Then these 4 parts has again been divided into 4 parts. Now my next step will be to again divide this into another 4 parts. Correct? Once I again divide it into another 4 parts, that means now I will divide 0 to 0.06 into 4 equal parts. Right? So it will become 0.015 like this. Not 0.15, sorry, 0.001. So you can calculate it. So this 0 to 0.06 will now be divided into 0 to 0.015, then 0.0162 like that. Okay, so I am mentioning this 0, but actually by 0 I am saying 0.1. By 0 I am saying 0.1. By 0 I am saying 0.1, not 0, because I cannot take 0. So now we are at the solar system. So super galaxy, 4-part subgalaxy, subgalaxy 4-part galaxy, galaxy 4-part solar system. Now the main part. So up to this our exploration is there. Now what is the fitness function that I can use to identify the optimal solution? I can use the fitness function because I am saying I want to maximize this y based on this x. So yn, if yn is greater than the previous one, yn minus 1, then I can go with this x, right? Then the x n minus 1 is worse than xn, correct? If xn, matlab yn minus 1 is less than yn, so xn minus 1 is non-optimal compared to xn, current one. So this is the fitness function that I will use to find the most optimal solution. And what are the values of x? You will enter the values of x as this one, 0.1 to 0.015. These will be your values of x. Matlab, the values in between 0.1 to 0.015 will be your values of x. One by one you put those values into x, note the values of y, compare it with the previous one, and you will get a new y. You compare the new y with the previous y. If new y is better, matlab greater than the old y, you go with, you have find a better solution. So on, but by experience I can say the most optimal solution can be received or can be achieved when x will equals to 0.015, because the x is 0.015 is the highest value among this domain, 0 to 0.15. Right, so certainly it will give the most maximum value of y. So this becomes the best solution of one of the subpopulation, right? And then from that part 0.016 to I think 0.030, I think you will find another best solution in x is equal to 0.030. Then from that, so this is a very simple objective equation. The maximum value of x will yield the maximum value of y because there are no other variable that exist. So that is why I can straight away say that the most optimal solution will be when x is equal to 0.99, correct? Because for this one, y will be maximum. But when there are many other variables like x1 plus x2 square plus x0 square, you cannot say like that. At that time, for x, there will be one solution domain, for x2 another solution domain, for x3 another solution domain, and so on. And the randomization, randomly division of solution space into sub-solution or population of optimal, probable optimal solution, and then to subpopulation, and then to solar system, and then to planet will take place for each of these x1. Each of these x's. That means x1, for x1, 1, for x2, another, for x3, another, and so on. Right? So at the end, what happens is, with the help of this iteration only, I can identify the best solution among all the subpopulation that I have created. And then once I identified all the best solution of a subpopulation, I will compare them with each other, and I will find the best solution of the population. Now there will be many more population also. So I will compare them with each other to find the best solution of the entire solution space. Right? So this is the way this algorithm functions. And this is also, you can compare this with the partitioning algorithms, where the solution domain is automatically partitioned, and according to the mean, media, mode, or like this, it is classified into different classes. So there, in case of unsupervised classification, you can use this galactic swarms search algorithm. Now, as this was a very simple equation with y is equal to x squared, so I can say by experience only that the maximum value will be at x equal to 0.99, right? But when it is complex, like I have explained, x1, x2, x3, then you have to use some such algorithm like particle swarm, genetic algo, and colony to find the best solution among the subpopulation. Then with the help of subpopulation, based on the subpopulation, you will find the best solution of the population, and from the population you will compare the best solution of all the population to find the most optimal solution that exists in this solution space. Thank you.